So this talk is about Arrow's impossibility theorem. It's a really fun, really interesting result in the mathematics of voting, like the theory, mathematical theory of voting. And so first we're going to have to talk about like literally what it means to vote and all the ways that one can choose an alternative, right? So like what is a voting system? Well, we'll declare a list of alternatives to choose between. So like if you're voting for something, you're normally voting between a few alternatives. And note, just like in the math club survey that just went out, you're not just always voting for the thing that's on top. You're actually making a total preference list, right? You're not picking the top thing, you're actually making your entire preference list. And we're going to actually include that in our voting theory. So our idea is going to be that our voting systems will informally, you could make this a formal mathematical definition if you want, involving Cartesian products of sets, whatever that means, but like you don't need the formal math at all to understand what's going on in this talk. So informally, a voting system should take in as input. So like every person is going to put in a ballot. So the voting system needs to know how to handle every possible configuration of everyone's ballots. So we'll take in a personal preference list of the alternatives for each person. So that's sort of what a voting system should take in as an input, right? Everyone who is allowed to vote should be putting in a personal preference list. And I should say, like off the bat, we're going to make two simplifying assumptions that can feel like one that should feel reasonably natural. And if they don't, please feel free to interrupt me. So the first assumption is that actually everyone's going to list every personal preference they have. So like they have to write everybody down in some order. So they can't just like say, no, I just care about the top alternative. I don't care about anything else. They have to list everybody. And we're not allowing any ties in people's preference lists. We're just going to make there are ways this can be avoided, but it just makes the theory slightly more complicated for an hour. So we're just going to start being like, okay, you have to arbitrarily break ties if you really think they're the same. And if you want, at the questions, you can ask me what happens when we allow for ties in the input. So we have this as our input, and then our output will, again, not just be a quote-unquote winner, but it will actually be a whole societal preference list, right? So it will return like what the voting system says society wants. So this is the entire framework of a voting system. So far, are there any questions? Cool, so let's go through some examples. So like example, who should be math club president? I just picked my two DRP students. I did not know that they were the president and vice president of the math club. So I picked Ryan and Shannon, so there's a set of alternatives, right? And we're gonna just assume for argument's sake that the people who can vote are the people who came in this Zoom call. So, you know, Ryan, there's a recall election, all this fun, and we all have to decide how we're gonna vote. Even with two alternatives, there's many ways we could vote, right? We could do what is traditionally known as first past the post. So what we all do is we decide whether we want Ryan or Shannon to be president, and then for argument's sake, we put the other person like below that in our personal preference list. We submit them, and then the societal preference list is given by how many times the person appeared as the top preference. And there might be ties in the output list. So it could be that they got the same number of votes. But even when there are two alternatives, there are many other ways we could choose, right? So let's say like the same as above, but the current president's vote actually counts for 2 votes. That's allowed, right? We're allowed to change each individual person's parameter. And in fact, like we're allowed to change people's parameters in potentially wonky ways. So here's a voting system with a name I just came up with, but it seems pretty natural. I call it last past the post. And last past the post is literally just ordering the societal preference list by who got the least number of votes, right? So who do people want to be president least? That's who we should get as the president, right? That's an absurd voting system, but by our definition, it is a voting system. And finally, another example of a voting system is my personal favorite, It's called the dictatorship, where I just get to vote. And so here's how this will work. Every single person in this call would put in their personal preference list. And then the way the societal preference list would be determined is that we'll just look at my preference list, and that will be the societal preference list. Now, I'm personally in favor of that, but maybe you guys are not. So there's sort of different properties that each of these voting systems have. And so we're going to talk about vocabulary kind of things that we can use to describe different kinds of voting systems. So the first kind of thing that you'd want in a voting system is something that's called the Pareto condition, which I believe is named after a person. The Pareto condition, well, I'll just put it as follows. The Pareto condition, I'll give you a second to actually read that, because I realize that's a lot of text. So the idea is that if every single person puts in the same personal preference list, then if your voting system is any good, then your societal preference list should be the ballot that every single person put in the preference list, right? This is a very weak condition. It's called the Pareto condition. So for example, first past the post satisfies the Pareto condition, because in first past the post, if everyone puts in the same ballot, then majority rules, quote unquote, says that we should get we should get that ballot as our societal preference list. Similarly, the thing I called weighted first past the post, there's a question in the chat if it's related to Pareto efficiency. I actually don't know. I'm not so good at actual economics. But I mean, I would imagine, because this is sort of the intersection of mathematics and economics. So I would highly suspect they are the same person, but I don't know. Thank you for asking. Anyway, and similarly, the dictatorship also satisfies this Pareto condition, right? Because if everyone in this Zoom call put in the same ballot, then I put in that ballot too. And dictatorship says we're just going to take my personal preference list and use it as a societal preference list. And so it definitely satisfies the Pareto condition. Finally, a non-example, an example of a thing that's not Pareto, is last past the post, right? If everyone votes, I don't know, Shannon over Ryan, and then the societal preference list turns Ryan over Shannon, that does not satisfy the Pareto condition. And I would like to thank again my two DRP students, Ryan and Shannon, for being my involuntary examples. Normally I would pick people in the room. Anyway, so here's another example that sort of can show you how when there's more than two alternatives, I should say, things could get even wonkier. So the new question that we're going to ask, instead of who should be the math club president, is who should get Florida's electoral votes in the year 2000 to be president? As a simplifying assumption, I'm going to assume there are actually only three candidates: George W. Bush, Al Gore, and Ralph Nader. So the usual way that we vote in America for most things is at least the state level, it's usually first past the post. Not always, but usually. Sorry, somebody have a question? Never mind. So in particular, we could pretend that everyone put in their full preference list, but if you've ever voted before, which you should vote if you're eligible, that you're rarely asked to rank all of your preferences. You're only asked to pick your top candidate. So we can just imagine that as we can pretend that everybody put in their full preference list and then just only think about the top entry. So if we do that, we have our election results, which are, so I should say, of course, the voters are Florida voters, and here are your election results. So you can see here that George W. Bush won this by what, 537 votes. And what is sort of interesting about this kind of election is it shows you that, at least it makes a strong case or some kind of mathematical example, that it's not the case that everyone will get their, how do I say this? Let me put it this way. If you happen to believe that everyone who voted for Ralph Nader, the third candidate, had their second choice be Al Gore, then the selection would be totally different. Now that's not so clear. Like it's hard to say why people vote for what they vote for if you don't actually take their personal preference list. So like you can't actually say things like, oh, everyone who would vote for Al Gore, I'm sorry, would vote for Ralph Nader would have had Al Gore as their second preference list. But it sort of shows you how close these things can be in a real world situation. So for example, I'll show you a different kind of voting system that we could have done with these three candidates. It's called instant runoff voting. And it's a thing that's actually being tried on more local levels around like the world, or I should say at least around America. I don't really know much about like the elections outside of America, but the idea is this. Let's say there are these three alternatives, George W. Bush, Al Gore, and Ralph Nader. The way instant runoff voting works is the voters will rank all three preferences. So for example, one might say, my hypothetical ballot earlier was Ralph Nader is number 1, Al Gore is number 2, and George W. Bush is number 3. And the way we do it is that we're going to declare, I'll write this down. We're going to declare that I'll say this slowly and put it on my slides. We're going to declare that the person who got the least number of votes on the, to be last on the societal preference list. And then on every single person's personal preference list, we'll erase the person who got last and just pretend and move everyone else up. And then if there's more than 3 options, instant runoff voting is still valid. We can just repeat, right? We could just keep applying the same scheme. And like you can ask yourself, could this have changed the results of the 2000 election? I caution you, from what little I know about people's personal voting preferences, I caution you to not conclude things so rashly, but it is definitely a mathematical fact that if everyone or indeed 600 more people had their full preference list as Ralph Nader, Al Gore, George Bush over Ralph Nader, George Bush, Al Gore, then there would be a different president in 2000. But this is actually hard to say, so I just caution you to not immediately conclude that, for example, everyone who would have supported Ralph Nader had Al Gore as second place. I don't think these things are so clear. But it's really interesting to think about how if we kept track of what people wanted, we might be able to get really a better option, right? It's sort of this crazy thing. You would sort of expect in a really good election system, not only would we, in a really good voting system, not only should we satisfy that cheap Pareto condition, which is so easy, right? Any voting system that anyone puts basically should satisfy the Pareto condition, at least for most things, right? That seems like a totally valid thing. One other condition you can ask for a voting system is for the voting system to be what we call independent of irrelevant alternatives. So I'm actually not going to give the formal definition of independence of irrelevant alternatives, just because I'll give you the informal definition in a sec. But I think it's a good idea to sort of remember that this proof also works on an informal level. We don't need the full language of function theory or unions or sets or partitions or induction to really understand what's going on here. This is a fact about people who do things. And it's sort of easier to picture in your mind people who do things. And it sort of helps with things like combinatorics, if you imagine them as people in real life and stuff. But I'll now give you I'll now give you the informal definition of independence of irrelevant alternatives. And then as an exercise, if you're really interested in this, I defined a voting system as just a function, a certain kind of function. You could define it using set theory as an exercise, and then define independence of irrelevant alternatives as an exercise. But again, you don't need the fancy set theory language to be able to describe what's going on here. So here's the informal definition. If for every pair of alternatives X and Y, so for example, in our Florida election above, there would be 3 pairs of alternatives, 3 choose 2, Bush-Gore, Bush-Nader, and Nader-Gore. For every pair of alternatives, we can know whether the first preference was larger than, equal to, or less than the second preference, i.e. the relative position of X and Y on the societal preference list. We can know that just from knowing the relative position on all of the individuals' preference lists. So what this informally is going to mean is that a voting system should only be allowed to look, if we're choosing between, for example, Ryan and Shannon, a voting system, and for example, I've decided to throw my name in the ring as president, as math club president. Now we're choosing between 3 alternatives, Shannon, Ryan, and I. But if we make, ideally, if we make a good voting system, it should have a property that if, for example, people want to choose Shannon over me, it shouldn't have to know how they feel about Ryan if they want to choose Shannon over me. The voting system should be able to tell people preferred Shannon to me without looking at what happened to Ryan. So that's independence of irrelevant alternatives in a voting system. What questions do you guys have about it?
Wait, so it's like if you do know that, let's say they prefer Shannon over you, does that mean that they wouldn't have to know if they prefer you over Ryan?
So what I see your question. So maybe I'll say this in a better way. So suppose like we wanted to know just on the societal preference list, we want to know whether Shannon and I are tied. Shannon is like greater than me, Shannon is more preferred, or Shannon is less preferred. The idea of independence of irrelevant alternatives is that if we want to know just that information, we should only have to look at Shannon and me on people's ballots. You could hand the voting system the ballots with all of Ryan's names erased, and it should still be able to tell, oh no, like definitely Shannon beat Tom. We saw that it's possible that the first past the post voting system does not satisfy independence of irrelevant alternatives, right? If we believe, which again is a highly contentious assumption, but let's say for theoretical sake, if everyone who voted for Ralph Nader preferred Al Gore second and everyone else preferred Ralph Nader third, we saw that actually in a different voting system, Al Gore would have won the election. And this happens like, in a rough estimate, this happens once every 20 to 30 years. So like, you know, you can go back in history and find more things of wonky problems that can come up when you have more than 2 alternatives in your voting system. So like this leads to a totally natural question. Like it seems like first past the post is like bunk. It's bunk because like it doesn't satisfy this seemingly easy property, right? So here's a question for you guys. Is there a voting system which satisfies both the Pareto condition and is actually independent of irrelevant alternatives? Take a second to think about it.
Also, I just wanted to clarify because I didn't catch the definitions at the beginning. Wait, so the dictatorship is just, even though you take everyone's ballots, your vote is the one that counts as the societal preference list?
Yes.
Okay. And then The weighted one is just that instead of counting once, every vote counts twice.
No, the idea was that we singled out a person. Like, for example, we could say like Shannon gets 2 votes and everyone else gets 1, and that's like a weighted first past the post.
Oh, so it's like one of the alternatives just gets more. It's weighted compared to the other ones.
Sorry, I should say that a voter gets 2 votes. So like your name's Dan, yeah, yes?
Yep. Yes.
So let's say in our hypothetical weighted first past the post, Dan, you get 2 votes, but you have to put in the same vote twice, and everyone else gets 1 vote. That would be like a weighted first past the post.
Oh, okay. Okay. Thank you.
No problem. Thank you for asking. By the way, while some of you are thinking about this, these slides are available on my website. The chat has the links, but I guess someone can put it again if they want. And like you guys should, I think you guys should feel free to not look at the slides I'm showing and to sort of hop around if you miss something. But you're also free to interrupt me, whatever works for you. But in the meantime, everyone's ranks. I see what you're saying. So someone said, what about a voting system where everyone ranks the candidates? First place gets 3, second gets 2, and last gets 1. The candidate with the highest point total wins. That's a great idea. You'll discover at the end of this talk that won't satisfy independence of irrelevant alternatives, which is a huge bummer. In fact, so I'll maybe tell you the answer now, unless anyone have a last minute guess. I'll give you a hint. We've already talked about it.
Guess.
Yeah, go ahead. Yeah,
Yes,
Charles is absolutely correct. The answer is a dictatorship. Because if, again, for a dictatorship, if say, for example, I'm the dictator, if everybody puts in the same ballot, the voting system will say, oh, let's look at Tom's ballot. That's a societal preference list. Great. That was the ballot that everyone put in. Now let's check that it's independent of irrelevant alternatives. Let's call the alternatives Shannon and Ryan again. Again, I really appreciate you two being such involuntary examples. If the societal preference list wants to know whether Shannon is greater than, less than, or equal to Ryan on the list, all it needs to know is whether it's the case on my list. It doesn't have to look at whether there were other people running and their election, like where they were on my list. If it just wants to know whether Ryan beats Shannon or Shannon beats Ryan or they tie, all it has to do is look on my preference list. So like, okay, unfair. People also don't want dictatorships. It's sort of a thing here. So like, are there any other like voting systems that satisfy these 2 conditions, Pareto and independence of irrelevant alternatives? And I think one of only 2 math facts that have given me a real-life existential crisis is the Arrow's Impossibility theorem, which says that the answer here is no. So I will read Arrow's Impossibility theorem to you, like as it's written right now. Assume that V is a voting system with more than 2 alternatives, which satisfies the Pareto condition and is independent of irrelevant alternatives. Then we know that there's someone in the set that's actually a dictator. So like, of course, a corollary of this is just what's called the contrapositive, or maybe it's not actually literally the contrapositive, but a corollary of this is that there are no voting systems with more than 2 alternatives, which satisfy the Pareto condition, a pretty reasonable condition, independence of irrelevant alternatives, a seemingly reasonable condition, and are not a dictatorship, another reasonable condition. So it's 5:34 in my time zone. I am willing to restart at 5:39 if you guys want to take a break. You guys can ask me questions, but if you guys want to get up for 5 minutes, I promise I won't continue content for 5 more minutes. And then starting at 39, whatever 39 means in your time zone, I will prove this theorem. But for now, what questions do you guys have?
I actually have a question. Are there any voting systems that satisfy the independence of irrelevant alternatives without the Pareto condition?
Yes. So one thing that you could do is you could do last past the post. So you like take everyone's ballots and you like invert them. So like, for example, I mean, and that satisfies independence of irrelevant alternatives, because again, for example, if you want to know, let's say you ask the societal preference list, was Ryan chosen over Shannon? Then you could look, and all you have to know is whether a lot of people chose Shannon over Ryan. I hope I inverted that. I should invert that. But yes, the answer is yes. So there's 2 questions in chat. One is, why can't we do instant runoff where every option's ranked? Just by the proof of the theorem, we will see that that somehow does not satisfy independence of irrelevant alternatives, but I don't have a specific example in my back pocket. Another person asked, why is independence of irrelevant alternatives important for a quote unquote fair voting system? And in fact, that's actually part of the interpretation of Arrow's impossibility theorem. It's that independence of irrelevant alternatives is like secretly asking for a lot. And in fact, it's asking for so much that like it's literally impossible unless you want a dictator. So like I was being like slightly facetious when I said independence of irrelevant alternatives is a good condition. It's a very hard thing to satisfy when there's more than 2 alternatives. But it definitely feels that way before you know the fact, right? Like at least when I first saw this, I was like, oh, yeah, like of course that, like, why hasn't a smart person just come up with a voting system like that? And the reason is that like there literally is none except a dictatorship, which, you know, has its own problems.
And then again, sorry for being repetitive, but it's just it's kind of hard to wrap my head around the independence of irrelevant alternatives.
Mm-hmm.
Okay, so you said that you only need to look at you only need to look at the relative position of X and Y on everyone's preference list.
Yes. You don't have to know if there's a third alternative Z. You can
Yes.
pretend like you don't know that. Like, and the voting system will still be able to tell you.
Oh, so it's like if there's more than 2 alternatives and you just want to look at 2,
Yeah.
then you should know which one of those 2 comes out on top.
Yes, that's a good way to put it.
Oh, okay.
Thank you
Okay.
for asking questions. It really is good that you like wrestle with these ideas, because that's how you learn. Go ahead. Sorry, I interrupted somebody.
Yeah, I'm still not sure how exactly that's a difficult condition to me. I mean, clearly it is, but I'm not sure how.
Well, I think the proof will be semi-enlightening. Like, yeah, definitely. I mean, I know conceptually it doesn't feel so hard, but like, we'll see that like we can really rig this to work, like, and really rig it to like some crazy conclusions.
There's a question in the chat.
Did I miss it? Oh, you know, what happened? Oh, so I think I answered these 2, and like, why can't we do instant runoff? I don't have a specific counterexample, but you'll see through the proof of this theorem that somewhere like you'll get caught. And why is independent of irrelevant alternatives more fair? I don't think it's more fair. I think the quote unquote lesson of this is that independence of irrelevant alternatives is a much bigger ask than you might at first think it is, or at least I first thought it was. I should say, for timing reasons, I guess I didn't realize there would be announcements, so I quote unquote plan to end at 6:05 or 6:10, but like I'm not in any way offended if you leave early, if you have to be somewhere. People like feel free to leave. I won't be mad. I'm not monitoring who's here or anything. But just a warning. There's a question in the chat. Is there a shorter phrase to refer to independence of irrelevant alternatives? I can talk very fast, so I never bother, but some people just write IIA when they're writing it. But all that's really important is that like it's clear from context. So if people are chatting with you, you can say IIA as long as you want, or you can use any word. The one that I've seen written is IIA, but I think that's not so, that's like, that sounds more like jargon. That's not what it is. It's independence of irrelevant alternatives. But anyway, I want to, in the next 20, 30 minutes, prove this impossibility theorem. But first, we're going to do like a warm-up proposition to just sort of get our minds around what can go wrong when we ask for these two conditions. So let's assume that we have a voting system with more than two alternatives that satisfies Pareto and independence of irrelevant alternatives. Then I claim that this voting system, oh, sorry, there's the statement I just said. And I claim that this system can produce no ties, literally none. So that immediately rules out first past the post. I think there was a question in the chat which was like, can my instant runoff thing do it? If your instant runoff thing could in any way produce ties, then no, this proposition already shows you're wrong, which is so crazy because you'd think it's like super clever and stuff, but yeah. So, and I also, so this, the proof of this proposition will take one slide, like literally this slide, I'll finish it, but I just have to sort of introduce you to my ballot notation. So here's the first statement. So let's pretend that we have a ballot and we want to know, we have two alternatives, A and B, and like watch carefully at the ballot as I say this, because this will be like important to reading the notation. If some group of people, which I'll just call the left side of the room, votes A over B, and the other group of people, the right side of the room, votes B over A, and the societal preference list ranks A and B equally. That's what this says. So I'm going to assume, for the sake of contradiction, that if I have a voting system with more than two alternatives, which like if I have a voting system like in the proposition, that if I'm going to say if it has a tie, then we'll find a contradiction somewhere. So let's assume that there's some alternatives A and B, where if some group of people, which I call the left side of the room, votes A over B, and the right side of the room votes B over A, it gives inequality in the societal preference list. Let's see what happens when we have a third alternative, C. So I didn't write this, but I'm going to say this. C is a third distinct alternative. So let's just do a warm-up. Well, I'll do the first one and you guys can do, well, you guys can talk about the second one. So let's see what happens when the voting system votes like this. So let's pretend that the same group of people, which I called the left side of the room, votes A over C over B. And the right side of the room votes C over B over A. So notice first that the whole group of people prefers C over B. Therefore, in our societal preference list, by Pareto and independence of irrelevant alternatives, our societal preference list will return C over B. But A is tied with B, so we get this societal preference list. This is a warm-up on the ballot notation. Are there any questions of what I haven't proven it yet, proven the proposition, but are there any questions on the ballot notation?
When you were talking about, you said C over B, the societal preference list was which one again?
This
C over B.
This is the one on the right. So like the way I view this in my brain is I pretend that the left side of the room puts in some ballots. And the ballots say, at least in part, there might be more alternatives, but they definitely say, I want A over C, I want C over B, and I want A over B. Like, well, that's implied. And then the right side of the room voted C first, then B second. Well, not necessarily first. We just know relative preferences, I should say. There might be a bunch of other alternatives, but independence of irrelevant alternatives says that like it doesn't matter. As long like we just to know the rankings of C, B, and A, we just have to know like where they are relatively to each other.
But then if C is greater than A on the right and A is greater than C on the left.
Yeah, then we might not know. We might not know what's going on.
Okay. But then how did you conclude that C is greater than B, which is equal to A?
So I did this in 2 steps. So let me just say what's let me just like literally start from the proof again. It's like literally only 1 sentence. I know it looks more complicated. So if we ever come, let's assume for the sake of contradiction that there is a tie. Then then there's some 2 groups that make this tie between some 2 alternatives. I'll call them A and B. If let's pretend like we just move some of the group of people to the left side of the room who votes A over B and the right side of the room B over A. And let's assume for argument's sake that if everyone on those sides of the room votes the way in the if statement, then the societal preference list will say A is equally preferred to B. That's what we're assuming. And then I asked a hypothetical question. What would happen if C is a 3rd alternative and the left side of the room voted in the way I wrote on the slide and the right side of the room voted the way I wrote on the slide? Well then, because everyone in the whole group, in both groups, voted C was better than B, Pareto and independence of irrelevant alternatives say that the societal preference list needs to return C over B. But we assumed already that B was tied with A. And
oh.
Transitivity, C is over A. There's a question in the chat. So do the 2 sides of the room have an equal number of people? Not necessarily. This is the best part, right? So in fact, if you want to get super theoretical, one side of the room could be empty. But then, and we'll talk about like what that really like means in real life, quote unquote. But no, the 2 sides of the room do not have to have an equal number of people. I'm just assuming that my voting system is some random function that satisfies like 2 conditions, Pareto and independence of irrelevant alternatives. And I'm already able to conclude some stuff about where C lies given certain voting patterns. So like, for example, the left side of the room could be like one person who like, you know, just has some crazy voting power, right? Like, and then the right side of the room could be everybody else. So let me ask you a question. Following the logic of my second line, what happens when the left side of the room votes A over B over C, and the right side of the room votes B over C over A? Think about it. So I'll give you a mild hint. Can you say anything about whether the society prefers B to C? Oh, shoot. Yeah. I tried to click the chat. So, yeah, absolutely, right? There was an answer in the chat was an awesome answer. And I told everybody I wouldn't say their name in the chat, but I want to reward you for saying a good answer. Oh, well. Anyway, the answer is this, right? Since everybody in the room, everyone in the whole group prefers B to C, then by Pareto and independence of irrelevant alternatives, B is definitely better than C in the societal preference list. But we again assume that A was tied with B. So we get this societal preference list. So that was a warm up, but like now let's ask ourselves a question. What happens? What is the second line, the one that says then? What does the second line say about if the left side of the room votes A over C and the right side of the room votes C over A? What does the second line say? Noting that it's independent of a relevant alternative, so we can forget that B ever was an alternative. I see an answer in the chat, which is awesome. The answer is the second line says that if the left side of the room votes A over C and the right side of the room votes C over A, then C is better than A. Now, here's a question for you. What does the third line say if the left side of the room votes A over C and the right side of the room votes C over A? The other way, right. I see an answer in the chat. So that's a contradiction, right? The societal preference list can't return that like one candidate is both greater than and worse than the other. So therefore, our original assumption was false that there were no ties. And therefore there are no ties because our original assumption was that there was two groups of people where if they voted this way, then the societal preference list would give a tie. Scary stuff. What questions do you guys have on it? How do we know that C is greater than A? So I said in the second line, which has then, I showed that if the left side of the room returns a ballot that has A over C over B, and the right side of the room has a ballot that returns C over B over A, then we use some like Pareto to show that C greater than B, but B was tied with A. Now, independence of a relevant alternative said that we only have to look at, when I want to know whether A is greater than C in the societal preference list, I only have to look at A over C up here. And similarly, if I like C over A should never know, can't know whether B was there, right? So I can just pretend that wasn't there. And so the second line says that if the left side of the room votes A over C and the right side of the room votes C over A, then the thing that will come out is C over A. Are there any other questions?
Wait, but then, so that first option comes from the second line and the second option comes from the third line, you said? Okay.
So maybe it's worth going through and just like saying one more time what happened in the third line. So let's assume that I want to know whether A is better than C, C is better than A, or they're tied in the preference list. I look at the third line. The voting system, when it wants to know whether A is better than C or C is better than A, isn't allowed to look at B. So all it sees when it wants to tell me if A is better than C is like A greater than C, C greater than A. But I already concluded earlier that that returns A over C. So the third line says that we have to get A over C, and the second line says we have to get C over A.
Okay, gotcha.
Are there any other questions? We found our contradiction, right? So therefore, there can't be any ties. So by the way, for everyone who asked, if your voting system has a tie, then like it cannot be satisfy both these conditions. This is a proof. So now let's talk about how we're going to prove the bigger arrows impossibility theorem. So we are going to call a subset of voters a dictating set if whenever everyone in the set puts the same ballot in, then the societal preference list that comes out is the same ballot that everyone in S put in, regardless of what anyone else votes. So for example, the set of all voters is a dictating set under our assumptions of Pareto and independence of irrelevant alternatives. Why is that? By Pareto, absolutely. Two people said by Pareto, and you're totally right. Like that, Pareto is by definition equivalent to saying the set of all voters is a dictating set. And note now, if S is a set with one element, then S is a dictating set if and only if the person in S is a dictator, right? If the set of one person is a dictating set, then by definition, the person in the set is a dictator. Because if they put in a personal preference list, then the list that comes out is a societal preference list. That's the definition of dictating set. So that shows the only if direction, and the if direction is pretty similar. So okay, I'm gonna make one more definition, and then we'll like just go right into the heart of the proof. So let's first make a simplifying assumption. Another assumption that you would reasonably expect your voting system to have. And by the way, we didn't use this assumption when I showed there was no ties. So already a lot of people's proposed voting systems are out. But let's assume our voting system's monotonic. What this means is the following property. If for every alternative, our voting system will be monotonic. If for all alternatives A and B, the following property holds. If one group votes A over B, and everybody else votes B over A, and then A over B comes out, here's the idea of what I'm going to say. Let's look at the people and everyone else. One thing they could do is they could change their vote. And the people on the side, everyone else could change their vote, and they say, oh no, I want A over B now. In a good voting system, that shouldn't change the result. If more people vote for A over B, then A over B should not come out. That B over A should not come out, right? It shouldn't switch if more people vote for the other thing. So that's exactly what this says. If some people in the everyone else part switch their vote to A over B, then the societal preference list still has A over B. So like you couldn't, if I wanted, I don't know, Ralph Nader to be president over George Bush, it is in my interest to vote Ralph Nader greater than George Bush, right? It shouldn't be in my interest to vote the other way. I think that's another reasonable property. And the idea is that this will just allow us to focus on the worst case scenario. So like now we won't just say like, all right, let's assume that the left side of the room votes one way. We can just assume worst case that everyone else votes against them and see what happens. This is not necessarily the statement of the, this is not included in the statement of the theorem because you don't need it to prove it. Prove Arrow's impossibility theorem, but it does make the proof slightly easier. Not too much easier, but slightly easier. And then I'm just gonna make one more definition. Oh, by the way, are there any questions on monotonicity?
Do we know if the left side is less than everyone else? Or if it's more than everyone else? Like, how do we know which one it is, I guess?
We don't need to know the size of groups.
Mm.
So like there could be one person and 100 on both sides. It's not like we split it in half. We just split it in some subsets.
Mm.
And so I'm just going to make one more definition called forcing, which is like should feel intuitive. And what I mean by that is not that you should easily understand it right now. What I mean is if you don't understand the definition of forcing and why it's called that, you should ask a question. Because like it's very easy to get lost in things that are quote unquote obvious. Believe me, I do that every day. Anyway, given two alternatives A and B, we say that a subset of voters can force A over B if everybody votes in S, A over B, no matter what everyone else votes, what should we get in the societal preference list for this definition?
A over B.
Absolutely, right? Like if they force A over B, it doesn't matter what everyone else votes, they get A over B. So that's the definition of forcing. Are there any questions on forcing? Cool. So, let me check the chat. What's the difference between forcing and having a dictating set? So forcing is for two specific alternatives. So for example, like if your fifth grade class is voting to go to a restaurant as a reward for good behavior, and they want to go to McDonald's or Culver's, a Midwestern treat that none of you might know about, then the teacher might be allowed, and like let's say like another, so like the choices are McDonald's, Burger King, or Culver's, a Midwestern treat. But let's say the teacher gets a vote and all the students get a vote. But the teacher hates Burger King. So what they can do if the teacher is feeling mean is they can put Burger King lower than, for example, Culver's on their preference list. And then no matter what everyone else votes, they'll definitely go to Culver's over Burger King. So forcing is just about two specific alternatives. The teacher's voting system might not have any power over McDonald's versus Culver's, but there might be two specific alternatives which you can force. But that's a great question. Thank you for asking.
Oh, like it's for two specific alternatives out of more than two.
Well, yes, and in fact, we're assuming that our voting system has at least three alternatives.
Okay.
Thank you for asking, all of you. So let's go for an outline of the proof. So here's how the rest of this talk is going to go. I'm going to outline the proof. I'm going to tell you a lemma and a proposition from which the theorem will directly follow. Then I'll prove the lemma and the proposition. Then I'll restate the lemma and the proposition so you can see it again. So I'm sort of doing like a sandwich. I'm giving you the bird's eye view first. Here's the lemma and the proposition we're going to prove, but you won't see why they're true. Then I'll prove that the lemma and proposition are true. So I'll zoom in, and then I'll zoom back out just to like make sure we have the conceptual picture, because this is hard to keep in your mind. But first, here's the two claims, right? So first is what I will call the forcing lemma. So I'll read this pretty slowly and deliberately. So if I have a subset of voters, which I'll call X, which can force A over B, and we partition the subset into two groups of people. So what this means is that just everybody is in exactly one group, so they can't be in no groups and they can't be in both groups. I labeled them L and M for left and middle of the room, just to like make things kind of easily move to personhood. If you can force A over B, then for any alternative C, either the group L can force A over C, or M can force C over B.
Why can M force C over B if?
Sorry, this is an or statement, but I'm just telling you the statement of the lemma. I'm not proving the lemma yet.
Mhm.
But it's an or statement, so I'm not saying that M can definitely force C over B. What I am saying is that if M can't force C over B, then L can definitely force A over C. And by the way, there's a small typo. This should say third alternative, I believe. So a third alternative different from A and over B. But we'll just keep that in mind in the future. And then the proposition, so I'm just giving you the bird's eye. You're not going to know why these two statements are true. In fact, they're like kind of counterintuitive, right? Here's the second one. So I haven't written the full statement out yet, but the statement is this. If a subset of voters X can force any element A, some random element over some random other element, then in fact, they can force any element over any other element. So forcing is actually equivalent to being a dictator, which is kind of surprising. Which of course means that X is a dictating set. So I'm going to say this again, but let's practice. Why would these two things prove the theorem? Well, first of all, our forcing lemma, we're going to make everyone who can vote go in the room. And then we're going to divide the room roughly in half, right? And then call that L and M. Then we'll see what happens when we feed in A over B. Or we'll see what happens if the left side of the room votes A over B and the right side of the room votes B over A. If A over B comes out, then the left side of the room forced A over B because everyone else voted B over A. But if B over A comes out, the middle of the room forced B over A. Oh, shoot, I should do this in a better way. Let me take a second and say that again. We'll start with everybody in the room and pick your two favorite alternatives and call them A and B. Everybody in the room, the set of all people, can force A over B. Now I will split my room in roughly half. We might have to break some ties, but it doesn't matter. The lemma says that either one side of the room can force A over C for a third alternative C, or M can force C over B. The middle of the room can force C over B. But this proposition says that if a group of voters can force some element over some element, then it's a dictating set. So we're just going to repeatedly apply the lemma, making the people that aren't dictators just leave the room. And then eventually, since there's finitely many people, we're going to have to whittle it down until there's exactly one person left in some set. And then we apply the same argument and we find, oh, look, X was a dictator. The set of one person is a dictator. And therefore, the set of all people is the set of that person is a dictator, or dictating set, and therefore that person is a dictator. So someone asked a question: is it possible that neither L nor M will force their desired results? And the answer is no, I claim, but I haven't proven yet. That's exactly what this forcing lemma says. The forcing lemma says if you have any subset of voters, then either L can force A over C or M can force C over B for a distinct alternative C. So I see now that it is 6:10. You can leave the talk knowing a very shocking thing already. If you have a voting system that satisfies Pareto and independence of relevant alternatives, there can't be ties. That's already an amazing fact that excludes a lot of people's proposed voting systems in the chat. I think just because like we don't have to reserve a room, people can leave when they want. I'm going to take another 5-minute break, pause for questions that anyone wants to know about, and just keep going with the expectation or understanding that if you have to or want to leave, I don't care. Like, I feel like you need to focus on your mental health first, and then fun math somewhere after. If they're not thinking about the irrelevant alternatives, you should vote for your mental health and your like your health and relaxation over math, with some irrelevant alternatives maybe mixed in. So I'm going to not move or not continue the talk until 6:15 or whatever 15 is in your time zone. Anyone, including the math club staff, should feel like they can leave, because I know how annoying it is when somebody talks a lot. But I do want to finish this and like put a video out for people who want to go through it again and again.
And you said the video would be on your website?
I'll probably post it on YouTube.
We'll also link to it on our website.
Oh, okay, okay.
So I had a question about the forcing lemma.
Great. Don't let me forget the question in the chat. Go ahead.
Okay, so I don't know if I'm misunderstanding the definition of forcing, but say you've got like X is 2/3 of the population.
Uh-huh.
If you then split it into a third and a third, the other 2/3 could form a voting block against the other one.
Yes, I see what you're saying. I'm saying in the forcing lemma that can't happen. Like literally, you can keep split. So like, yeah, you can keep splitting. You can keep splitting, and this exact thing, this voting block, won't happen. And I'll show you that in the lemma.
Okay.
Like I'll show you like a slightly stronger lemma, basically.
Wait, but you were saying, Joshua, you were saying that if you take 2/3 and then you split that 2/3 into each of a third,
so
they can force something on the rest of the 2/3.
Let me just give you a preview of what I'm going to say.
Mm-hmm.
Like, so here's the ballot. I've included a case for L, a case for M, and a case for everyone else.
Mm-hmm.
So does that make you happy, person that asked the question? Like, does this like make your case feel better?
I'd have to take a closer look at it, but
Sure.
Yeah.
I'll go back. How do I go back? I click these rewind arrows. Now there were questions in the chat that I'll answer. So there has to be a subset of X that can force something in X, so there has to be a dictator. That's absolutely right. And the reason is this: our starting subset of the voters is the subset of all voters. A great tip that carried me far in my first 2 years of undergrad was that if you have a set, the empty set and the whole thing are both count as subsets. So the first subset we're going to use is we're going to say, well, like if everyone votes one way, by our Pareto assumption, then the ballot has to be that way. So X can force, like the set of all voters can force anyone over anyone. And then our methodology will be just like, oh, we'll keep dividing the room and finding smaller and smaller dictating sets. And again, I haven't proven either of these statements yet, but I will in 1 minute, unless anyone has any questions. I'm a very approachable, fun, likable guy.
I was just a little bit confused by the wording on that question. So it's like, so there has to be a subset of X that can force something in X.
Like, so, yeah, our starting assumption is by Pareto.
Yes.
So and then like we're just gonna like keep spamming both of these, this lemma and this proposition, and just be like, oh, but we can find a smaller dictating set because of that, and we can find a smaller and a smaller one and a smaller one, right?
Yes. And then you just get down to one dictator, I guess.
Yeah, the set of one person is a dictating set, therefore that person is a dictator.
Okay. Yay, dictatorships.
Okay, so let's prove the forcing lemma. So I've just written the forcing lemma again for you. If a subset of voters, which I called X, which doesn't have to be the whole voting, doesn't have to be all the voters, can force A over B, so for some two alternatives A and B, and we divide the room in any way we want, then for any other alternative C, this again should say third alternative, L can force A over C, and M, or M can force C over B. We don't know which. But let's consider this ballot. And by the way, it might help to first pass, follow this proof line by line and verify that every line makes sense, and then come back to it later and see the conceptualness. But here's a question to make sure you guys are still following. For me to make sure you're still following, because if you're not following, it's not your fault, it's certainly mine. Let's assume that the ballots are like this. What can you say about the relative preference of A and B? There's an answer in the chat. The answer is absolutely correct. We can force A over B by assumption that X can, the subset L union M can force A over B, but we don't know where C lies yet. So let's break it up into two cases. In this ballot, we'll either get C is first, or we'll get that A is less than C. Because either A is, like either C is greater than A or A is greater than C, because again, we argue that there are no ties in such a voting system. So I broke it up into two cases. Let's check each case individually. If the output is C over A over B, then, well, let's see. Well, I claim that M can force C over B. Can someone say why that is? From the ballot up here. By the way, a verbal or chat confirmation, please. I have a mouse hand. Can you guys see my mouse hand?
Yes.
Thank you. So I'm saying if everyone votes this way, and the output happened to be C over A over B, then we just showed that M can force C over B. Yes, the answer in the chat is absolutely correct. Only the set of people which I denoted M chose C over B. Everyone else chose B over C. And therefore, M can force C over B. Because, again, we said forcing is about whether you can vote one way, and if everyone else votes the opposite way and your way still comes out, then you've by definition forced. And the thing I called monotonicity right here is just saying, oh, if L changes their vote to make B over, to make more people vote for C, then there's no way if more people vote for C that B over C will suddenly appear. Chat, does that answer your question? we smuggled, okay, thank you. By the way, thank you all for asking questions. You really only learn this way, I think. So we did one case, either the output is C over A over B, and we showed that M forced C over B. Now let's see what happens if the output actually instead in the other case was A over C. So here's a hint. What happens if one group of people votes one way and everyone else votes the opposite, but the output goes with the one way, then they forced? So can you find a group of people that voted A over C where everyone else voted C over A? I see in the chat, both chats are correct. L can force A over C, right? A over C, because L voted A over C and everyone else voted C over A, but we assumed our output has A over C. So L forced A over C. Okay. So now let me ask you something. Can we gain any more information from this proof when M is empty, meaning there are no people in the middle of the room? And I'll give you a place to look, right? Look at, can the empty set force anything? So if no one votes C over B and everyone votes B over C, can C over B come out as the societal preference list? So I see a question in the chat. What if the group I labeled everyone else voted differently and changed the results? Wouldn't that mean that none of the groups could force on their own? So what I'm implicitly using in all of these cases is independence of irrelevant alternatives, right? So this ballot right here, let's assume like A over C comes out. Then what this says is that if L votes A over C, because it's not allowed to know that B was there, and everyone else votes C over A, because it's, again, not allowed to know that B was there, like, and by, oh shoot, by everyone else, I mean M union the set I called everyone else, apologies for that, then L got its way. And I assumed monotonicity, meaning that if some people change from C over A to A over C, but the result was already A over C, people can't change their vote to A over C and still win. Like, people can't change their result to A over C and have C over A suddenly come out. Chat, does that answer your question? But everyone else could change to A over C and A comes out. Yeah, I totally agree, right? So I'm assuming I'm in this third case where the output returns for this ballot, which could have other preferences that are irrelevant. I'm assuming that this ballot returned A over B and A over C. I'm on the third line. And we don't know anything about what B or C's relative preference. But let's see what happened if everyone else, the quote unquote set called everyone else, changes their vote from A to C. But I already know that A over C came out. So my assumption of monotonicity was that if the set I called everyone else changes their votes, that just like can't change the election to A over, like it can't change this alternative A over C to C over A. Yeah, another person in the chat says no matter which way everyone else votes, L is still a forcing set. And the answer is absolutely yes. Because again, my assumption of monotonicity allows me to just consider the worst case scenario. And I showed you in the worst case scenario that assuming the output is A over C, then L voted A over C, everyone else voted C over A, and yet assumption A over C comes out, and therefore L can force A over C. So here's again the question, can we gain any more information from this proof when M is empty? Like, so there's no one in the middle. And in particular, I asked you, can C win if no one in M vote, like no one votes the way that I wrote M, like if M is the empty set? Can C over B win?
No. No.
No, absolutely not, right? Because if M is the empty set, then everyone voted B over C. And therefore, B over C must win. So like, therefore, like L must be able to force A over C for any third alternative C. Similarly, what information can we gain when the set of voters I called L is empty? What information can we gain about forcing A over C? Like who will win if L is the empty set? A or C? C, absolutely. Everyone who answered is totally right. So that's just something that we'll keep in our back pocket. And I'll call this the forcing lemma for the empty set, which says that if a subset can force A over B for two distinct A and B, then the set can force A over C and C over B for any third alternative. That's just the two empty set cases I said above, right? Because then if X is partitioned into X disjoint union the empty set, I get that X can force A over C. And similarly, if I let like X be in the middle, be M, then it can force C over B. But then a corollary of this is that if X can force A over B for any distinct A and B, then X can also force B over A. And again, I just recommend you verify this line, the proof I'm about to show you line by line, not try and think of the conceptualness, because I'm just spamming the forcing lemma for the empty set. So proof. By assumption, the proof that, let's assume X can force A over B. So by the forcing lemma for the empty set, X can force A over C, where C is a third alternative. Because X can force A over C by the forcing lemma for A over C, then X can force B over C. And because X can force B over C by the forcing lemma for B over C, then X can force B over A. I just spammed the forcing lemma 3 times, and I was able to reverse the order. If X can force an alternative A over an alternative B, then X can force an alternative B over an alternative A. So there's 2 slides left, proof of the proposition, and then a review of the 2 things we showed, and which will prove it.
Ooh.
Is there a question?
Yeah.
What's up?
So I'm not sure I follow this part, just
so
in general.
Let's just follow it again line by line.
Yeah.
So if X can force A over B,
Yeah.
I use the forcing lemma for A over B to show that X can also force A over C, right? That's what exactly verbatim what the forcing lemma says.
Mhm.
Now I'll use the forcing lemma with B and C swapped. So now it says if X can force A over C, then X can force B over C, right? I swapped B and C. Therefore, but the forcing lemma for the empty set says X can force B over C. And now I'll use the forcing lemma where B is like A is replaced with B and B is replaced with C. I know it's wild, but I promise if you permute the letters, this will work out. The forcing lemma then says when you switch in the way I said for B over C, then X can also force B over A.
Wait, but why does A over C force B over C?
A over C forces B over C because of the forcing lemma. If a subset X can force A over C for two distinct alternatives A comma C, then X can force A over B and X can force B over C.
Mm-hmm. Okay.
I promise you, if you permute the letters, you will see it fall out.
Mm-hmm.
And in fact, that's going to be an exercise. If use this same logic to show that if X can force A over B, then for any distinct alternative C and D, X can force C over D.
But not D over C.
And D over C, right? Because, well, I didn't have to say that, right? Because if you pick your favorite actual things for those letters, I can pick the opposite things for those letters. And this proves our proposition, right? Which said that any subset of people that can force A over B for alternatives A and B is a dictating set. And so that proves the forcing lemma and the proposition. So we've actually proven our theorem already, but just for some kind of conceptual framework, we'll review what we proved. So review, we showed the proposition, which was that if you can force some alternative over some other alternative, then you're a dictating set. And we showed that the forcing lemma, which was just that if you divided your room, then one subset of the division can force something. So that subset has to be a dictating set. And so now, again, we just keep dividing the room and finding the dictating set between the two. Like if there's 100 people in the room, you could divide it in half. You could also pick one person on the left and 99 in the middle or something. Whatever works for you. But either way, we've proven Arrow's impossibility theorem. Thank you guys for coming and thank you for sticking around. What questions do you have?
What is?
I'll
sorry.
turn off the recording for questions. So give me a sec.